Alright, we're going to go do a little tutorial on aromaticity. First we're going to find out what are the criteria for being aromatic. So it's two things. The first of which is that it must have an uninterrupted cloud of pi electrons, be cyclic, planar, so flat, and every ring atom must have a p orbital. Right? That's the first one. So benzene's kind of our classic example. It's in a ring. Every one of these carbons is sp2. That means it has a sp2 hybridized, which means it has a p orbital. It's cyclic and it's flat, right? And this is kind of what it looks like. You can see the pi cloud above and below, kind of like a sandwich. And here is the uninterrupted p orbitals, right? All these p orbitals lined up, that p orbital system. The other criteria, number 2 here, is the pi cloud must have an odd number of pairs of pi electrons, or electrons in this pi system. So it means you need an odd number of pairs. So if you look at the benzene, there's 1, 2, 3 pairs. So that's an odd number of pairs of pi electrons. Cyclic, uninterrupted pi system with p orbitals and an odd number of pairs. Those are the two criteria. Now, not everything is aromatic. Things can be something called anti-aromatic as well. So anti-aromatic. So aromaticity is something when something is very stable. Anti-aromatic would mean something to be very unstable. So the criteria for anti-aromatic is the same as aromatic, that it has essentially an uninterrupted pi system, right? So this has an uninterrupted pi system, right, in a ring, uninterrupted pi system in a ring. But in this case, in anti-aromatic, it has an even number of pairs of pi electrons. So that's bad. So here we have 1 and 2. So this is cyclobutadiene. So this would be considered anti-aromatic, right? It's cyclic, planar, has an uninterrupted pi system with p orbitals, but it has an even number of pi electrons, of pairs of pi electrons, which is bad. Now cyclooctatriene, this, you might expect this to be anti-aromatic, but actually it's non-aromatic. So if you can avoid being anti-aromatic, you will. Just like you will try to be aromatic, you will try to not be anti-aromatic. So this is actually non-aromatic. And the reason that is because this ring essentially puckers. So if it was flat, right, here's an uninterrupted, there is p orbitals on all these carbons, but it's saying, well, I have 1, 2, 3, 4 pairs. That's an even number of pairs of pi electrons. That's bad. So I'm going to not be planar. I'm going to be puckered and prevent myself from lining all up, which makes me non-aromatic then. So there's another picture coming up that's better. So, like I said before, right, if you look at this, you'd think cyclooctatetraene is planar, right? You'd think it'd be 1, 2, 3, 4, and you would expect it to be anti-aromatic, but it's actually, again, non-aromatic. And it's non-aromatic because it refuses to be planar. It'd rather not be anti-aromatic. So you can see here, the bonds essentially pucker. It bends up and forms kind of like a cup. So these p orbitals are no longer all lined up perfectly. So it's not an uninterrupted pi system. So it actually moves itself so it becomes not, so it's no longer anti-aromatic and just is a non-aromatic. Right? So if you had a choice, you would avoid being anti-aromatic, just like you would try to be aromatic. Right? So they're not delocalized. Right? It bends itself so it has like a cup shape, so the p orbitals are not all lined up. So then it becomes non-aromatic. So some other examples of non-aromatic and aromatic compounds. Right, again, aromaticity requires an uninterrupted pi system. If you have an sp3 hybridized carbon, you immediately cannot be aromatic or anti-aromatic, so you're just non-aromatic. Here, I would say actually this one, the cyclopentadienyl cation, is not aromatic. I would almost call this one anti-aromatic. Why would I say that? Well, this is anti-aromatic in my opinion because it has an uninterrupted pi system. Right, sp2 hybridized carbon, so a p orbital here, all p orbitals, uninterrupted pi system, and has an even number of pair of electrons in that system. So I would consider this anti-aromatic, which is the same as saying not aromatic, but really I would consider this one anti-aromatic. But now instead of having a plus charge here, if you put a lone pair in, right, you still have an uninterrupted pi system. Right, this carbon is going to choose here to be sp2 hybridized to have a p orbital, and that's where this lone pair is going to go into a p orbital. And then that will be part of a pi system, which has 1, 2, 3 pairs of electrons in it. So now this would become aromatic. Right? So if it doesn't have a p orbital, it can't be aromatic or anti-aromatic. If it has an even number of pairs of pi electrons, and it's an uninterrupted pi system, it's anti-aromatic. And if it has an uninterrupted pi system and it's an odd number of pairs of electrons, 1, 2, 3, then it's aromatic. So now what happens if you have a heterocycle, right? Something within a nitrogen, oxygen, and sulfur, something with the lone pairs in the ring. Now how does that work? Right, same rules still apply again, right? Rule 1, uninterrupted pi system, right, of p orbitals, all lined up. That's number 1. Number 2, an odd number of pairs of p orbital electrons, right? Okay, so our rules still apply. So now here we look at this. This is a ring. This nitrogen has a pi bond, so we know it's sp2 hybridized. So it has 1, 2, 3 pairs of odd, so it's an odd number of pairs of p orbital electrons. So that would be aromatic. Now the question in here is, what about this lone pair? That lone pair would be in what molecular orbital? It would actually be in an sp2 orbital. So that would not be part of the pi system. It's an sp2 orbital. To be part of the pi system, you have to be in a p orbital. P orbitals form pi bonds. So to be part of the pi system, you must be in a p orbital. Let's look at this pyrrole. Now this nitrogen right here. Normally this nitrogen, right, if I normally showed this to you, normally this nitrogen, we would say that is sp3 hybridized, right? It has no pi bond, so it's sp3 hybridized. But in this case, this nitrogen is going to choose to be sp2 hybridized. Now why would it choose that? It's going to choose that so this lone pair will be in a p orbital. Right? By being sp2 hybridized, it has a p orbital. Now putting that lone pair in there creates an uninterrupted pi system, and with that lone pair in there, it makes it be an odd number of pairs of electrons in that pi system. So 1, 2, 3. So that makes this aromatic. Similar case over here with oxygen. It's going to choose to be sp2 hybridized. And one of these lone pairs, right, one is going to be in a p, and one is going to be in an sp2 orbital. So one is part of the pi system. This one's part of the pi system. This one's not. But again, 1, 2, 3, so that makes this aromatic. Exact same deal with a thiophene. One lone pair would be in a p orbital. The other one would be in an sp2 orbital. And the sulfur itself would be sp2 hybridized. So the sp2 orbitals, here and here, these electrons are not part of the pi system, so they're not part of the resonance forms. They're not delocalized. Right? And the nitrogen, oxygen, and sulfur here are choosing. They're making that choice to be sp2 because it puts the lone pair in a p orbital in all these cases, which then can be part of the pi system, which then makes the whole thing aromatic. Here are some good pictures. I like these pictures because they show the orbitals. So here you can see the uninterrupted pi system, and here you see that one lone pair in that pyridine, right? So this is what pyridine is, to recalibrate ourselves. So they're showing this lone pair right here, which we said is in an sp2 orbital, right? That's showing it right here, right? See how this sp2 orbital is not, right? This sp2 orbital is not part of the pi system, right? All the pi electrons are here, and this sp2 electrons in that sp2 orbital are not part of the pi system. They're perpendicular 9 degrees away. All right? Contrast something like the pyrrole here, right? Which was this example. Now, its lone pair we said was in a p orbital. Notice that's where it's at, right? Because it's part of the pi system. By putting it in there, you have 1, 2, 3 odd number of pairs of electrons in the pi system, and this NH, right, is perpendicular to it. Now, furan, a little different. Now there's 2 lone pairs. Remember on this oxygen, right? Of course, still sp2 hybridized. Right, it's sp2 hybridized. Box it in. One lone pair is in a p orbital. The other lone pair is in an sp2 orbital. Right, so you can see one lone pair is in a p, which is part of the pi system, making this aromatic. 1, 2, 3 odd pairs, uninterrupted pi system. The other lone pair is in sp2 orbital, and it's perpendicular, not part of the pi system. So this could not be stabilized by resonance or pushed into the ring with resonance. Some more complicated, maybe more examples with these heterocycles. So you can start to see these. Right here, this is nitrogen. This nitrogen is sp2 hybridized. And that lone pair is not in a p orbital, it's in an sp2 orbital. Right? It's not part of the pi. So this lone pair here is not part of the pi system. This lone pair here is not part of the pi system. Now with indole, again, the nitrogen is going to be sp2 hybridized. But this time, that lone pair is actually going to be in a p orbital and be a part of the pi system because it's going to have 1, 2, 3, 4, 5, an odd number, which would make it aromatic, an uninterrupted pi system. Imidazole, you got two nitrogens. Now, both these nitrogens are sp2 hybridized, but this one's lone pair is actually in a sp2 orbital, not part of the pi system, where this lone pair is actually in a p orbital and part of the pi system. Again, aromatic though. 1, 2, 3, it's aromatic. Uninterrupted pi system. Purine, even more fun. Now you can start to see this is in an sp2 orbital, not part of the pi system. sp2 orbital, not part of the pi system. sp2 orbital, not part of the pi system. p orbital, part of the pi system. Right? So these are all sp2 hybridized, but where the location of the lone pairs is different for each. Well, these are sp2s. This is p. So 1, 2, 3, 4, 5. Odd number. So this is actually part of the pi system, whereas these three are not. Pyrimidine, similar thing. Both these nitrogens are sp2 hybridized, and these lone pairs are both in sp2 orbitals and not part of the pi system. So now to summarize all of this, just to remember, aromatic compounds become aromatic because it's more stable. Right? A cyclic compound with localized electrons is always going to be better than anti-aromatic. Anything with anti-aromatic is bad, right? So cyclobutadiene, right? A cyclic uninterrupted pi system with two or an even pair of pi electrons is bad. That's going to be anti-aromatic, which is always going to be less stable. Right? Aromaticity is all about stability. Anti-aromaticity is all about instability. Right? So something like this, again, I think, right, this would be an uninterrupted pi system, an even pair of electrons. This would be anti-aromatic. So both of these molecules are not very stable. Right? Aromatic, most things are non-aromatic, and then anti-aromatic things are things that are stuck in those rings that have the even pair of pi electrons, pairs of pi electrons, and those would be really unstable. Aromaticity itself is all about stability.